Um, yeah, welcome everyone. Again, my name is Asanka. Or at least one of you may know as me as Adam in a previous lifetime. So yeah, here's a talk about salary workers in Kubernetes. It's not specifically Django per se, but it's if anyone's working with Django, they're likely to have at least worked with Celery or heard of Celery. So and Artem thought this is a talk that I've done internally at CG. So Artem thought it could be something that's interesting for the meetup as well. So this is generally a talk about Celery itself, a little bit of introduction of what Celery is, what it does, why it's used, and the journey in our team, how we go to sort of stabilize how Celery works within our infrastructure. So yeah, I hope you enjoy it. So what's contained here is few things about Celery. What does it solve? Like a sort of like a beginner's introduction if you haven't used Celery at all. How do we use it in Cover Genius? And then we get into a little bit about Kubernetes, how it's implemented, and how we sort of solved our scaling problem that we had. All right. So let's get into Celery itself. So the general problem is so web apps are getting complex. As we all know, response time is important to our users. Everyone's impatient, and if the web app is doing many things, what can we do to make it faster? Is usually if something can be delayed, and that's where background tasks come in. So if you're doing sending SMSs, generating PDFs, or whatever in the background, and you can pass it on to a different task, and you can respond back to the user with whatever you need to do, your response time is quicker. So that's what Celery does in general. So this is just basically from the Celery documentation. It's a simple, flexible, reliable, distributed process to manage your workloads. So real-time processing, supporting task scheduling. So it's not just based on the applications, the tasks that you push through, but also like a cron job. You can actually have a scheduled set of tasks that runs in the background. Okay. So going a little bit into Celery, it's a unit of work is a task. And we have worker processors in Celery that monitor the queues and pick up the task to perform. And Celery manages this communication via messages. So you'd have a broker that mediate the messaging between the clients. So your application would push a message through to a broker, and the Celery worker will pick it up. Yeah, so the client adds a message, the broker delivers that message to a worker, and once a task is completed, we can have the status reported back and optionally save it to a backend as well. And yeah, this another note is that sometimes it's common to use the same backend as your broker as well as the results backend, but it doesn't have to be, can be different things. Some of the tools that's used, Redis is pretty common in the world of Celery. RabbitMQ, Kafka, and I heard SQS as well just a few moments ago from Fred as an experiment, that SQS or some other tooling. So there's many other tools that's available for you to use as a broker. So it can consist of multiple workers and brokers to make it easier for you to scale your application better. So Celery, it's written in Python, but this can be implemented in other languages as well. So you could potentially use Celery in different stacks. A very simple diagram of what Celery could look like. For example, if you have a fast API, client that pushes Celery tasks through to a broker. In this example, we have Redis as the broker as well as the results backend. And that's where you have your tasks queued up, and the workers will pick up the tasks, process them, and send the results back to the backend, which can be used by your application. So what else is there? So apart from Celery, some alternatives, RQ, it's called, I think Redis queue is the short, the RQ is short for Redis queue. Very simple scheduling or background process application. There is also Dramatic and Huey as some of the alternatives. And this is mainly in the Python world, but if you're looking at other stacks, there's this Beanstalk and Laravel queues in the PHP stack. I'm sure there are other solutions in different stacks as well. So after that quick introduction to Celery, I just wanted to give you a quick brief on how we use it. And then this is just a simple command. Once you have the Celery app configured, this is where you sort of use Celery command as your package and your Celery app name and initiate a worker. So doing so will sort of give you a similar or this kind of output if you're running a test on local, for example. And as I mentioned earlier, you could have a different database. For example, we are using Redis here as a transport broker as well as a results backend, but it's, you know, in Redis, you could have different databases, and this is using a different database in Redis as your sort of results backend. In CG, we use Grafana as our platform of choice to look at most of our systems, and you know, this is a sample of a dashboard that we use to observe what's going on with our Celery workers. Sort of going into HPA or horizontal pod auto scaling in Kubernetes. So in Cover Genius, we use Kubernetes. Anyone else here use Kubernetes in their application? No? In the past, yeah. Okay, good. So yeah, Kubernetes is a you know, I'm not going to sort of go into what Kubernetes is yet. So horizontal pod autoscaler is I guess one of the tool sets within Kubernetes that allows you to scale your pods in a based on metrics you have. So as mentioned here, so it's if you have a deployment or a stateful set, these are terms from Kubernetes. The horizontal pod autoscaler allows you to sort of manage your workloads better. So within Kubernetes, you have the HPA, which observes the metrics that you have, and it will manage your deployment into however many pods that you want to have, depending on your configuration. So the HPA uses a simple algorithm to figure out how many pods you need. This is what it is, and I'll come back to this a little later when we show some of our examples and why this matters as well. So in our infrastructure, this is a very simple outlook of the specifics when it comes to how we have HPA configured in our Python application web-related pods. So essentially, we specify the minimum number of pods that we want to have and maximum number of pods that we want to have, and some triggers in metrics. So for web pods, depends on memory and CPU. The more requests that your application receives, more things it has to do, the more memory or resource consumption it'll go through, which will trigger a scaling event, and it'll scale the pods. Very similarly, workers, we also use memory and CPU, but not just that, we also use a custom metric, Celery task latency. So once a task is picked up, how long it's actually waiting for it to be processed. So if the application is doing a lot more things, and this task latency is triggered, that also tells the HPA, the Kubernetes, to scale the pods and have more pods available to use background tasks. So that's what we have. So how does it work, and how do we actually do that scaling effectively? So this is sort of our journey. And so what's our problem? So increased background tasks. So we have some monthly renewals that happens. So this is based on the number of policies we have. So we had about 3 million records to process, particularly based on a new client who wanted to do sort of monthly renewals. So good problem to have, but nonetheless, it was a problem. So we had a few delays, increased errors due to sort of unnecessary retries. So related internal services. So in Cover Genius, we use multiple services in different teams, and those teams were affected. And what we thought of doing is that, okay, we have a lot of background tasks. What can we do? So increase the number of maximum workers that we have. So all right, let's just jump in, and that's what we did. As you can see, so we had this pattern of tasks going up and down, and at what point it got stuck, and we increased it again, and well, that sort of helped us to survive that time. But it wasn't great. So after this this event, we realized, well, the Celery workers are behaving in a particular way that it actually jumps up and down, jumps up and down, right? So I started talking to some of the infrastructure team members here, added a few more panels to understand what we are actually looking at, and yeah, just wanted to do a little bit more observations and experiments around how this works. So zooming into some of this, so we kind of realized, well, this is, for example, this is per second task number averaged over a minute. But we're close to 100 workers. So 30 tasks per second isn't that many, given that tasks are processed fairly quickly, and doesn't really need 100 workers. And not only that, I started sort of logging into some of the pods to investigate the logs, and most of these pods just spin up and process one task, and sometimes no task, and spin down. So that didn't make sense. And that's where this algorithm comes in. So you have this current replica number multiplied by the current metric value and desired metric value ratio. So if we're looking at a particular metric, and if you have triggered your HPA based on a particular setting, that can drive your desired replicas value to be a quite high value quite quickly. So task latency was our metric. So this is sort of like a histogram value that can be represented as sort of like a value between 0 and 10. So based on this value, the workers jump up, and they're necessarily not doing anything. They spin up, spin down. So as our first attempt, we changed the target. So instead of looking at a very small increase, we increased a bit more. So close to a second we can wait. We increased again when that didn't help. So 1.5 seconds of task latency. not much of a change. That didn't really change much. We still had the same problem. The trigger point was different. So 1.5 seconds, it still triggers and still goes up to 95 workers. That's when we noted something else. So I started digging into some of the other code that's around our Kubernetes infrastructure. So in Helm charts, so I'm not going to sort of go into Helm charts, but Helm charts are something that helps you manage your Kubernetes workloads. It's probably like a package manager for Kubernetes. It helps you to get up and running quickly. And I've noticed that the scale down had a policy defined, but the scale up didn't have. It was empty. So scale down had a policy to control how the pods would scale down, but scaling up didn't. So that was sort of like a moment of realization that we should have done this first. So we added a scaling policy so that the workers are added in a much more controlled manner, and that actually made a difference, right? That's sort of our first effect. We still we are able to manage the same workload with a less number of workers. So rather than sort of jumping up really quickly, as soon as the trigger flows, the workers would scale slowly, and it'll give us enough time to manage the workload. But there was a problem though. So as you can see there, the trigger point and the actual point of this scaling up happens, there's probably about a 5-minute gap there. So that's something that we wanted to work out as well. So when the next month came around to handle a few million records, that went quite smoothly. So instead of jumping up to 95 workers every now and then, managed to hit around 20, 30 workers, which was quite good. So in general, it was okay, but that delay was not really ideal. So I thought let's fix that. So starting the latency trigger is there. The initialization of sort of worker increase is about 5 minutes late. So when you start looking into this scale up policy, I realized I just copied and pasted from the scale down policy, and there's this stabilization window, which is something that Kubernetes uses to stabilize how it scales up or down rather than just going up and down very quickly. So yeah, based on the documentation, it's just a value that's there to restrict the flapping of replica count. So when that changed, I'll go up again. You can see the trigger point and the increase of workers came into an alignment, which was something that we wanted. And things are generally looking good afterwards. One thing to note here is the task latency is now around 8, which used to jump to 10 quite often. The fluctuations were still a bit much, I thought, and thought, do one more update. And that was to sort of increase the minimum number of replicas. So it jumps up and down every now and then because we have enough tasks coming in. So increase the minimum replicas, reduce our target a bit more now that we have a little bit of control on how we scale our workers, reduce the actual target of which we're looking at. And I also increase the stabilization window, so it takes a bit more time, because when these workers spin up, they take some time for sort of fully warmed up and start picking up workers. So if your scaling happens again, before the worker is ready to pick up tasks, then there's no point really. By the time the additional workers come in, the other workers already done the work, so they would just spin down. This generally fixed the problem, as you can see. So stabilized a lot more, and our latency dropped down, and it stayed around the 4 mark. This is just a scale of 0 to 10. Used to jump to 8 and 10 quite often, and stayed around the 4 value. So on average, most of the tasks, the chart on the right hand side, bottom right, is the amount of workers, sort of the latency taking over 5 seconds. So usually used to be a lot more workers waiting for more than 5 seconds to be executed. I should say tasks, not workers. But this is in general. We still time to time can get different values or spikes in tasks or worker numbers. So yeah, as I mentioned, quite a low latency value there. So what are the takeaways? So how many workers do you need to manage your workload, really? I mean, do experimentation, the least amount of resources you need to meet your SLAs, SLOs, whatever is what I would recommend. So if you don't have to spend on resources, don't spend on resources. And this is not just for salary, right? Like any other resource. I think the learning here is not just salary, anything else that you can use this principle on and observe and experiment with your resources. As long as you can manage your workload with less amount of workers, it's overall better, in my opinion. You spend less on infrastructure. So some other noteworthy stuff around here. So if you are using Celery or any other background worker, start monitoring them. You generally can do with a metrics exporter. So if you have a Celery exporter or something like Flower, you can start monitoring how your salary works. You can observe some of the patterns and see, sort of try and understand why it does what it does. And trying to understand if you are having a lot of workers spawned, trying to get an understanding of the logs from those workers and see if they're actually doing work or they just spin up and stay there. And using the correct metric. So this is important. So what metric do you use to scale your salary workers is quite important. Task latency is generally better. We also use queue depth. So if you have an understanding of how many workers you're getting into your queue, that also works. There are some downsides to that, whereas if you have an error and if you push a retry, the retries will go back to the queue as well, increasing your queue depth. In general, we have a preference for task latency, as in when the task was scheduled and when it got executed. So that sort of delay gives us an idea of how the application is performing. Yeah, this is something important to note. So the in CoverGenius, what we have used so far is the latency metric. So we use something called Celery Exporter for our metrics, and that exports the latency at salary level. So that depends on other things like what's your concurrency, what's something like there's something called prefetch multiplier when you sort of invokes salary workers. And those numbers come into play. If we can actually get the latency metric at the broker level, so if you know how long your task is waiting at Redis, that's probably a better metric. Right now, I'm working with the infrastructure team to sort of work out if we can actually use that metric going into the future. Setting up proper scale-up, scale-down policies for your pods. Have a look at your stabilization window and also have a reasonable value for termination grace period. So when the salary pods are scaled down, Kubernetes send a kill signal to take the pod down, but you need to have a good understanding of how your tasks are working in general and sort of what's the maximum number or maximum amount of time one of your tasks would take to complete. You may not get it right all the time, but if you have an understanding, hey, there's this particular task usually takes 1.5 seconds to 1.5 minutes to complete, then you would set your termination grace period to be about 2 minutes. That way, when the kill signal is sent, it still waits for those tasks to complete. Otherwise, you generally tend to get sig-term errors across your application. As I mentioned earlier, coming back to the latency metric. So this is what Celery knows. It doesn't show metrics about the tasks that are not yet acknowledged or picked up by the worker. This depends on concurrency and prefetch multiplier limits. I would love to show you an example, but setting that up and going through the examples actually take a lot of time, and you'd have to wait for 5 minutes to sort of stabilize the thing. So that's why I didn't want to do the live demo here. Instead, I sort of relied on the screenshots that I had. So looking at the metrics from the broker would be actually better if we can do it, in my opinion. And sort of that, the difference there is that right now our latency metric is based on the worker picking up the task and the application processing it. That is really our application's performance, not how fast we are actually picking it up or how many tasks we actually push to the queue. So if we have a set, if the task is predictable, so let's say we have a task that takes 10 seconds, we know that, and that's the only task our system has. And if we know our concurrency and prefetch multiplier, regardless of how many tasks you have in your queue, this latency metric will not go up because this is based on how many it's picking up, and that's set by your concurrency and prefetch limits. So if we can actually look at the latency at the broker level, if we use that metric, then I think that would be a better way of scaling the workers than what we already have. That concludes this talk. Thank you, and I hope you enjoyed. Hopefully you don't have any questions, but if you do have any questions, I will do my best to try and address them.
I have a question. So the thing is that Celery is definitely more applicable than RQ, right? And the thing is that it's like you can kind of subclass some Celery stuff, and you can configure Celery's own scale-up stuff. But that's if you rely on Celery's own scaling stuff, that's kind of on the machine old, from 10 years ago kind of a thing. However, it's like right now you also have these task groups, right? You can have task priorities, task groups, and you can have different classes of workers. Maybe that's a CPU bound worker. This is a worker that requires a lot of memory, and you can route them, accordingly. Does Celery let you compute a task group at runtime somehow, based on heuristics? Is that even possible?
Maybe, I don't know. If anyone else knows the answer, feel free to jump in. I don't know. We actually use a single queue. And we actually just had a discussion with Artem this afternoon about potentially having multiple queues in the future as well.
From my understanding, that should be
in my understanding, I'm not sure. Maybe, like you said, it's a lot of options to configure, and with that comes with a lot of complexity as well. I think, and your understanding of Celery can vary. So from what I know, you can actually configure multiple queues, and if you have good enough task routing, you could then potentially address your scaling policies depending on your queues. So you could target a particular queue. So you could have some background task that you don't care when it finishes in 2 seconds or 1 hour, whereas you'd have other tasks that you're really important, right? So if you can split that up that way, and then you can have your scaling policies look at those certain queues, that would be probably more efficient way of using your resources as well.
It's definitely possible now. I remember that in the past we tried the queues. We used those queues were priority based, but definitely you can route a Celery task to a specific worker to process. And then, yeah, maybe use different node groups in Kubernetes where you attach this workloads to. That shouldn't be too hard, but yeah, as Asanka mentioned, it's probably the complexity overhead is not worth it in our case. But if you have queues that do very complex compute operations, maybe that makes sense to do.
And also one thing to note there is priority. I think sometimes you configure priority in Celery. In my experience, sometimes it's the priority is not what you think it is. It depends really on the broker as well. Even on Celery documentation, they go on to say a few things about how priority is working. So like, for example, if you're using RabbitMQ as a broker, that's got broker level priority that you can set, whereas Redis doesn't have that kind of configuration in task settings. So
Redis broker for some reasons buggy because we tried it basically, so it would just run things multiple times, especially when you have a delayed test. And then when we shift it to active MQ, everything.
Yeah, so it really depends on the broker in your configuration. So I actually did have a different slide when I did the internal presentation about the simplicity of Celery. It's not as simple as you might think, even though they say it's simple. It's actually a great tool, but yeah, comes with some complexity as well. Yes?
It was interesting that you mentioned.
Maybe
Just repeat the question, yeah.
It was interesting that you mentioned that you considered using, or you were using a mix of the latency, the task latency, and the queue depth. But you said the reason why queue depth wasn't great is because the retries and stuff gets put back on the queue. To me, that was more of reinforcing. Isn't that something you'd want to scale based upon more, the queue still getting longer, whether they were original tasks or retried tasks? And secondly, wouldn't that be a stronger metric because it's a leading indicator? You know how long the queue is early, but you have to wait until the Celery task is picked up to know how long it's been waiting in the queue.
Yes. So to answer the first part, yes. The reason I mentioned it's using the retries as well, it was probably situational for us because we had some of our retries that were actually incorrect, as in we should not have retried on certain type of errors. So in our situation, we instead of having 100 tasks, we had 1,000 because we had 10 retries configured for some tasks. So, but yes, you're right. So the more if you have an understanding of queue depth, then that'll help us scale better. The internal argument I'm trying to sort of convince the team is that how many workers, like if you're purely working on queue depth or how many tasks you have in the queue, how do you decide the number of workers based on the number of tasks you have? So what's the proportion? What if you have millions of tasks coming in, what's the limit there? So there are certain arguments that's made, but I think if you have proper scaling policies in place and min-max resources, yes, in my opinion, looking at queue depth is probably more accurate, or we could use more proactive scaling. So yes, this is what I'm currently pursuing with the infrastructure team. Any other questions? If not, I'll hand over to Iqbal for the next talk.
maybe while